Hello and good afternoon, friends. Welcome to CEC EduSet live lecture. Dear friends, in this session today we are going to talk about modern physics. What modern physics is, we would try to understand about it, and I would like to tell you all that we would be talking on this particular topic for 2 days. I mean today itself, as well as we would be conducting another lecture on this very topic which we would be conducting tomorrow. And for this we have with us in our studios Dr. Mohammad Mudassir Hussain. He is Associate Professor in Department of Applied Physics, Jamia Millia Islamia. So first of all, I would like to welcome our guest, Dr. Hussain, and with the help of his immense experience, I believe that we would be able to understand what modern physics is. Welcome to the EduSet lecture, sir. We have heard a lot about physics, but first time the term modern physics appears something new to me. So what basically modern physics is?
Actually, like here we'll be talking about physics for small like particles, microparticles. Okay, like we know that you can apply Newtonian mechanics on bigger bodies, but what happens when you go for smaller system for the microparticles? There we'll see that a new type of theory we have to apply. We cannot apply this Newtonian mechanics there. So in this introductory lecture, we'll be talking about the idea of photon, then we'll try to see photoelectric effect, how to explain photoelectric effect, and then Compton effect. Okay, so here what happens that like light, we all know it behaves like a wave. But when we try to explain this photoelectric effect or Compton effect, or black body radiation, you cannot explain it by considering light as a wave. So in this lecture we'll see what is photon, what is photoelectric effect, why we cannot explain photoelectric effect by considering light as a wave, and Compton effect.
So over to you, sir. Let's start with the lecture on the modern physics.
Okay, so as I have told you, this is an introductory lecture. So the first important thing about this is that we all know about light, and this word light, it we not only mean visible light, but the radiation in the entire electromagnetic spectrum. Now this electromagnetic spectrum, it starts from radio waves, then microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. So the wavelength of radio waves is quite large. It is of the order of, say, you can say kilometers. Then microwave, it's of centimeter. So as we move towards the right side, towards gamma ray side, the frequency increases or the energy increases. Now all these regions like radio waves or microwave, we need a detector. It is the only small part which is visible, which I can detect. So, and this region lies between 400 nanometer to 700 nanometers. Now, we all know that this light, it shows reflection, refraction, interference, diffraction, polarization, and scattering. Reflection, we all know that when we shine light on a plane or shining surface, the light gets reflected. Then refraction, when this light passes through a denser medium like glass or water, then refraction takes place. And interference, we know if we have two coherent sources, these are coherent sources, the light, the waves, they interfere, and it gives us interference effect, the dark and bright fringes. Diffraction is also like when light passes through a small opening or a small opening or some obstacle, so you can see the diffraction pattern. Similarly, polarization and scattering. So the experimental result of all these phenomena can be very well explained by considering light as a wave or wave theory of light, governed by Maxwell equation. But there are other physical phenomena like photoelectric effect, Compton effect, and blackbody spectrum. The experimental result of all these cannot be interpreted by considering light as a wave or the model fails or breaks down. Now, we'll talk about photon. So, photon in 1905, Einstein suggested that light sometimes behaves as if energy is concentrated in a small bundle that he called quanta. We call them as photons or particle. The energy of photon, we all know, is given by h nu, where h is Planck constant, and the value of this h is 6.63 into 10 to the power minus 34 joule second, or we can express it in terms of electron volt second, that is 4.14 into 10 to the power minus 15 electron volt second. Now, this photon, it is just like a particle. It not only has energy, but it has momentum also. The relativistic energy expression for a particle like electron or proton, whose rest mass is m, like if you have electron or proton and the rest mass is m, is given by the relation E square is Pc square plus mc square whole square. Now, since photon moves with the speed of light, and we all know if something is moving with the speed of light, the rest mass is 0. So, we can put this m equal to 0, and then this E becomes equal to Pc. Now, this h nu we can put in place of E, we can put h nu, and this is equal to Pc, and from here we can get P is h nu over c. This nu over c, it can be written as 1 by lambda, because we all know that c is equal to nu lambda. Now, we can see from these expression from the previous one, E is equal to h nu, and from here P is h over lambda. Now, E is proportional to nu and P is proportional to 1 by lambda, or inversely proportional to lambda. Now, we can see on one hand we can see particle, and on other hand we can see a wave. So, the characteristic we all know of a particle is energy and momentum. We all know that if we have a particle, so there is a energy of a particle and a momentum if it is, say, moving. Now, to a wave we assign wavelength and frequency. So, the electromagnetic spectrum, these are the typical wavelength of this electromagnetic spectrum. So, we have radio wave. So, radio wave, the wavelength of radio wave is around 1 kilometer, and the energy, if we calculate this energy, it comes out to be 1.2 nano electron volt. Then we have microwaves, and the wavelength of microwave is of the order of centimeters. So, if we say 1 centimeter, it comes out to be 120 micro electron volt. Then we go for infrared, which is 10 micrometer, and the energy is 120 MeV, milli electron volt. Then for visible, it's 550 nanometer, and the energy comes out to be 2 electron volt. Ultraviolet is 100 nanometer, the energy is 12 electron volt. I mean, there is a region of all these, but we are considering the, say, order. Then X-rays, which is 50 picometer, energy is 25 keV, and gamma rays, the wavelength is very small, it is of the order of femtometer, and the energy comes out to be 25 MeV. Now, the photon idea was revolutionary in the sense that we all consider light as a wave, which is electromagnetic, and all of a sudden to say that it behaves like photon, it was a very, you can say, a bold idea which was suggested or proposed by Einstein, and even Planck, who introduced Planck constant in physics, accepted the idea slowly, and Einstein was awarded Nobel Prize in Physics in 1921 for photon theory. Now, there is a small problem here, and we will try to calculate the wavelength and momentum for this. So, the problem is like this, that during a radioactive decay, a certain nucleus emits a gamma ray, whose photon energy is 1.35 MeV. Now, we want to know what is the wavelength for this energy and what is the momentum for this photon. Now, we know that C is equal to nu lambda, and from this we can see lambda is C by nu. Now, this is a convenient way we can write, we can multiply this numerator and denominator by h, and we will get hc by E. Now, since energy is given in MeV, so we will try to write this value of h in electron volt second. So, we will write the value of h, which is 4.14 into 10 to the power minus 15 electron volt second, and the speed of light 3 into 10 to the power 8 meter per second, and then we divide it by 1.35 into 10 to the power 6 electron volt. Now, here we have given the conversion unit. We can generally write energy in electron volt and mega electron volt. In nuclear physics, we will write in terms of mega electron volt, and the conversion factor is 1 electron volt is 1.6 in 1.602 into 10 to the power minus 19 joules. So, in this way we can calculate this wavelength, and it comes out to be very small, which is 920 femtometer, which is very small. Then same way we can write momentum also. A momentum can be written as E by C from the previous equation we have seen, and the same way we can write this energy in mega electron volt, then we have to convert it into joules, and then we can get the momentum. So, this is a simple problem. Now, the problem is the photoelectric effect. The photoelectric effect, as we know, it is a very simple phenomena, and the result, the problem was that we were so used to this wave theory of light that we have in mind that light, it behaves as a wave, and we try to explain everything with that understanding. But the problem is when this experiment was done and we got the results cannot be explained by considering light as a wave. So, first of all we will see what is photoelectric effect, and then we will try to explain it by considering light as a wave, and then we will see that if we try to explain it with the help of wave theory, we fail to do so. But if we apply the photon idea that was proposed by Einstein, then you can easily explain the results of photoelectric effect. So, let us see what is photoelectric effect. Now, if you have a clean metal surface, and this is that surface is exposed to say light, and the conditions are right, we see the electrons are emitted. So, this is a small, this is the experiment, like here there is a vacuum tube, and in this vacuum tube there is a plate P and a collector cup C, and this tube is made up of quartz. It is because the domain or the range of photoelectric effect is visible and ultraviolet. We can cause photoelectric effect by visible light or ultraviolet light, because the work function of metal surface is of the order of that, let us say 2 to 5 electron volt. Now, the quartz tube is used because in the ultraviolet light it can pass through this quartz tube, and this glass tube it block this ultraviolet light. So, this plate and this cup, and there is a ammeter and there is a voltmeter, and we can change the voltage across this, the plate and cathode. There is a sliding contact here. So, when light is incident, on this metal surface or the plate, or you can say the target, and one thing more, we have to create vacuum also in the tube. Otherwise, if there are molecules of air, these electrons will bounce off. So, we have to create a vacuum also. So, when light falls on this, as we know, the electrons are emitted. So, when electrons are emitted, we can slide this contact, we can make it toward positive end or to this negative end, making the cathode positive or negative with respect to plates. So, as soon as the electrons are emitted, if we apply positive potential, this cup it collects these electrons, and when it collects these electrons, so the circuit is completed and current flows. We can see or we can detect current in the ammeter, and if we move this contact towards the negative end, the cup it becomes negative with respect to plate, and they will repel the electrons, and then these electrons they will not complete the circuit and current stops. So, towards sliding the contact towards negative end reduces the current, and sliding this contact toward the positive end, the current start flowing in the circuit. Now, we will see the result of this. So, here we can see in this figure, we can see the current and this potential difference. This is a plot of current versus potential difference, and at two different intensities. So, what we have done, when we have increased we have used the intensity of light and then we increased it. Now, we can see here, if you apply negative potential, the current reduces, and at certain potential the electrons are moving towards the plate. We have applied positive potential. Now, what we are doing? We are moving it toward the negative side. We are moving toward the negative side. So, that means we are applying negative potential. So, it will stop the flow of current and the current decreases. These electrons, they have kinetic energy, and what we are doing? We are applying potential energy, and since we are giving negative potential, they will try to oppose the motion of these electrons, and the current reduces, and at certain potential the current becomes 0. Now, we can see this is V0, this is the stopping potential. The electrons are moving, and we applied this negative potential, and at some potential the fastest moving electrons, they will stop. This is called the stopping potential. Now, what we are doing? We are increasing the intensity. Suppose we double the intensity of light. So, by increasing the intensity of light, we can see the current increases on the positive side, and when we are applying negative potential, the current decreasing, and then we are getting the same stopping potential. That means, just by increasing the intensity, the stopping potential remain same. So, this is one of the problem. The second is, here we can see that the maximum kinetic energy is equal to EV naught, because EV naught is the potential electric potential energy, and K maximum is the maximum energy of the electron. So, the important point here is that V naught remains same. If you keep on increasing the intensity, the stopping potential is same. This is the second plot or second figure, which is plotted between stopping potential and the frequency. So, we have used different type of light starting from say visible and then ultraviolet, and then we have plotted this graph, the intensity graph, and then we can see here that there is a frequency nu naught. Below this frequency, there is no emission of electron. The stopping potential is 0. I mean, stopping potential 0 means since there are no electrons, no stopping potential is needed to stop it. So, there is a characteristic frequency nu naught above which photo emission possible. So, these are two important things. Now, we will try to explain this with the help of wave theory. Now, and then we will land into some problems if we try to explain with the wave theory. So, what are the problems now? The problems are the problem of intensity. There is an intensity problem, then there is a frequency problem, and there is a time delay problem. What is the intensity? Suppose we are considering light as a wave, and this is a electromagnetic wave, and it has got electric field and magnetic field which are perpendicular to each other. Now, the intensity in the wave theory is, or in wave model is, that the intensity is proportional to amplitude square. If you increase the amplitude of electric field, the intensity will increases. So, just by increasing the amplitude of electric field, the intensity is increasing. You can see on the next figure on the right side, the amplitude of the wave is increased, and obviously the intensity of this is more. Now, intensity problem is that when we are increasing the intensity, we are increasing the electric field vector. When we are increasing the intensity, or that means we are increasing the electric field vector. Now, force is equal to Q times E. So, when you have a surface here and the wave, you incident wave on this, and the intensity is less, okay, so it will impart less force on the electron and the electron will come out. Now, when you are increasing intensity, you are increasing the electric field vector. Okay. So, when you are increasing the electric field vector, that means it is imparting more force to the electron, and the ejected electron will come out with greater force. So, with less intensity, the electron will come out with lesser force or lesser energy. So, that means you need to apply a small opposing force to stop it. When you are increasing the electric field, or when you increase the force is increased and it will come out with a larger force, then you need to apply large opposing force. That means opposing force is stopping potential. For less intensity, you need less this force, the stopping potential. For more intensity, you need more force. So, this thing has to be clear. But as we can see here in this graph, when we are increasing the intensity, the stopping potential is same. That means there is some problem. Now, if we consider the photon model, so the photon model is intensity in photon is that you are increasing the number of photons per unit area. So, here in this picture we can see that on the left side, suppose there is a beam, and this beam contains small number of particle or photons, so intensity is less, and on the right side we can see more number of photons are there, so the intensity is more. Now, if we explain with this, that with the particle model, so in particle model, intensity, less intensity means less number of photons per unit area, and higher intensity means more intense, more number of particles. Now, if we go back and see this, so here we are increasing the intensity. We are increasing the intensity means we are increasing the number of photons, but the energy is same. So, all of them, they will come out with same energy, but since the intensity is more number of photons will emit more electron. More electron means more current, but since they are coming with the same energy, same stopping potential is applied and you can stop them. So, with the help of here intensity means more number of photons, but with same energy. Now, these more number of photons will come out, they will emit more electron, more current, but the energy of these outgoing electron is same. So, you need to stop, you need a same stopping potential. So, that is why the stopping potential is same. So, this can be easily explained. Now, the second is that there is a characteristic frequency. Below this you cannot emit, or there is no ejection of electron, there is no photoelectric effect. Now, what wave theory says? Okay, you can increase the amplitude of the wave, and since the amplitude of wave is increased, the electric field vector is increased, the force is increased, and you can even with microwave you can emit out this electron. What you have to do is you have to increase the intensity, but what the experiment says that there is a characteristic frequency. Below this there is no emission of photoelectrons. So, this was the second problem. Now, again this problem can be solved with the help of this particle theory. So, this particle theory says that it is a kind of collision, and these electrons, they are bound to the metal surface with some work function. Now, it is a kind of collision. So, if the energy of the incoming particle is more than the work function, the work function means the energy with which the electrons, they are bound to the metal surface. So, if the energy of this particle or this photon is more than this, there is a emission of electron and photoelectric. If this energy of this particle or incoming this photon is less, there is no emission. So, h nu is the energy of the photon, and if it is greater than the work function, so there is a photoelectric effect will occur, and if it is less than that, it will not occur. So, these two things can be easily resolved if we try to explain with the particle model. Now, the third problem is the time delay problem. Now, we know once you shine the metal surface with the light, immediately we will see the current in the circuit. There is no time delay between shining it with light and detecting the current. There is no time delay problem. Now, if we take wave theory and if we take the wave theory and the intensity is say less. So, suppose we have a beam of light, and here you can see we have shown this atom and there is a electron. Now, if the intensity of the light is small, that means we are considering light as a wave and the intensity is less. So, this electron it will absorb this light, the energy, and then it will come out. And if the intensity is low, it will take some time, some large time, and it will absorb energy, and then it will, that means it will soak energy and then it will come out. And if the intensity is more, it will absorb energy more and then immediately it will come out. So, in the first case it will take some time because the intensity is low. So, it will take some time to absorb the energy, but in the second case, since the intensity is more, it will soon absorb the energy and it will come out. But we see there is no time delay whether the intensity is more or less. So, this was again a problem, and again this problem can be solved if we consider the particle or the photon model. Now, this photon model, say it is a kind of collision between two bodies. So, as soon as you shine light, and since the light consists of particles, so immediately there is a collision and there is a ejection of electron, or electron will come out. So, now we have seen that this theory, particle theory or photon theory, it very well explain photoelectric effect, which cannot be explained by the wave theory. Now, this is the photoelectric equation. H nu is the energy of the photon, the incoming photon, and this work function, this is the energy with which the electron is bound to the metal surface, phi, and this energy is shared by this electron. So, some of the energy it will dislodge the electron from the metal surface, and rest of the energy will be the kinetic energy of the electron. So, we can write this H nu is equal to the work function plus kinetic energy of the electron. Now, the maximum kinetic energy the electron is coming, we have to apply a negative potential, or with kinetic this kinetic energy has to be balanced with the potential energy. Potential energy is EV naught. So, we can write this kinetic energy when the electron it stops, we can write this kinetic energy equal to potential energy. So, H nu is equal to phi plus EV naught. So, now we can write this as V naught is equal to H by E into nu minus phi over E. You can write this equation, and now this equation is like y is Ax minus B. So, it is a equation of a straight line with intercept, negative intercept. So, what we do now, if we take frequency, different frequency, and then we calculate the stopping potential. So, this is the graph of stopping potential with the frequency. On x axis frequency is plotted, on y axis the stopping potential. So, we get a straight line and it gives a intercept. So, from the slope of this we can the slope of this will give us h by E. That means, from the slope we can calculate the Planck constant, and from in the intercept this is phi by E, this is equal to intercept, and from here we can calculate the work function. So, this is one problem which cannot be explained by wave theory, and this can be easily explained by the photon model. The second effect is Compton effect. Now, this is another experiment, and the experimental result of this Compton effect is again we cannot explain with the help of wave theory. And the importance of this experiment is that it is a great convincer for the reality of photons, and it because for the first time the momentum energy they were used into experimental situation. Initially this was postulated that they have energy and momentum, photon has energy and momentum, and we have seen also, but this was really used in this experimental situation. So, that is why it becomes more convincing that this light it behaves like photons, like particle. The second thing is the domain or the region of photoelectric effect. Or photoelectric effect takes place in visible and ultraviolet region. Now, this Compton effect we can observe Compton effect in high frequency region, that is in X-rays or in gamma rays. So, this Compton effect it extended the idea of photon to high frequency region, or we can say that the photon idea is not restricted to visible and ultraviolet, but it equally applicable to high frequency waves also. So, this experiment this was done in 1923 by Arthur Holly Compton, and he arranged a beam of X-rays of wavelength lambda to fall on a graphite target, and he measured as a function of wavelength the intensity of scattered this radiation in different direction, and this is the simple experiment for this Compton effect. These are the collimators, and these X-rays, they are incident on a target. This and after scattering, these scattered X-rays, they were detected by this detector, and this detector, it measures intensity as well as wavelength. That means we can move this detector at different angles, and then we can record the wavelength and the intensity of the scattered radiation. So, we have here monochromatic X-rays, and this is a target of graphite carbon material. Now, these are the experimental results of Compton effect. Now, we can see this intensity on y-axis, and on x-axis we have wavelength. So, when phi is 0, when we observe this straight through, so when the angle is 0, so we see a single peak, and this wavelength is same as the incident one. Now, if we rotate this at say some angle, say 90 degree, so then we can see two peaks. One is at the original wavelength and other at the scattered wavelength, and this wavelength lambda dash is more than the incident one. Now, if we increase the angle, suppose now the angle is more, so you make it say 180, so we can see the wavelength of scattered radiation is now larger. So, the wavelength is increasing, again we have two peaks. So, the problem is how to explain this change in wavelength, the lambda dash peak. Again, if we try to this delta lambda, which is the difference between the large wavelength, the scattered one, and the incident one, this is called as Compton shift, and this Compton shift, it depends only phi. Now, again there is a problem to explain this. If we try to explain this with the help of say wave theory, or we consider these X-ray to be a beam of waves or like electromagnetic waves, we cannot explain the lambda dash peak. But if we consider the photon model, we can explain the lambda dash peak as well as the wavelength peak. So, let us first try to understand, try to explain this lambda peak or this lambda dash with the help of wave theory. Now, what we have in this carbon target, we have atoms, and we are considering this light which is coming, we are considering as a wave, electromagnetic wave. As we have seen previously, it has got electric field. Now, there is a electric field vector, and in this wave, the incoming wave, it falls on the target has got atoms. So, when it strike this target, so these atom, they have the electric field. So, this electric field of this electromagnetic wave, it interact with the field of this electron, and these electrons, they started oscillating. So, when these we know from this electromagnetic theory, when these electron, they oscillate, they also emit electromagnetic waves. So, it is this atom of this target, it is acting as a small antenna. So, when you incident this wave, so it set the atoms into oscillations, and the electrons there, they will oscillate and they will emit a wave of the same frequency or same wavelength. Now, the wavelength is same, but what we see in experiment, that there is a longer wavelength in the scattered one. So, that means we cannot explain this by considering this X-rays as wave. But now, if we consider this X-rays to be that it is coming in the form of photons. So, what we have? We are considering now collision between two particles. We have atoms and we have electrons all around, and the inner electron, they are tightly bound, and the outer electron, they are loosely bound. This we all know because of screening and because of distance also. So, when this photon is coming, this outer shell electron, they collide with this and they get a kind of kick, and that photon, it transfers some of the energy. Now, we are saying that there is a transfer of energy and momentum, as we were saying in the beginning, that in this experiment we really have momentum energy transfer in experimental situation. So, what is happening? So, when the photon is coming, it will strike the outer shell electron, it will impart some energy to the electron will get a kind of kick, and then this photon will go away with the lesser energy, like we have seen in case of collision. So, that means since the photon is had imparted some of energy to the electron, it is going out with lesser energy or more wavelength. So, now we can easily explain why there is a change in the wavelength. Now, the next thing is then how to explain this peak which does not change. There is a peak at original wavelength or the wavelength of the incident X-rays. This also we can explain because the inner shell electron, they are tightly bound to the nucleus, and when a photon strikes the inner shell electrons, since they are tightly bound, and these electron till now we are saying free electrons or loosely bound electron, but these are tightly bound. Now, they are tightly bound, and when this photon, they strike the inner shell electron, the atom as a whole get a kick, or we can say there is inner shell electron, we have to consider the mass is more for this electron, or we can say the effective masses, we have to consider the effective mass, and the effect in case of carbon target, the effective mass of this inner shell electron is 22,000 times the mass of electron. So, that means they are massive, and when this photon comes and strike the inner shell electron, then the atom as a whole get kick, and the energy or momentum is not imparted, and they go out with the original energy. So, we get a original wavelength. So, that way we have two peaks. So, now we have seen that if we consider the photon model, we can easily explain photoelectric effect and Compton effect. Now, we can do the formulation for this also. There is a photon, incoming photon, and now we have considered a free electron. So, the photon will hit this electron, and the electron will then recoil, and the photon will go away with the lesser energy. So, E is equal to h nu is the energy of incident photon, and the momentum is h over lambda, and for scattered one, E dash is the energy which is less, and it is equal to h nu dash. Same way, momentum P dash is equal to h over lambda dash. The energy is reduced, and the electron will recoil at some angle, say theta. So now like in collision, we can resolve or we can write down the conservation of energy and conservation of momentum equation. So this is the first equation is h nu is equal to h nu dash plus m c square into 1 upon 100 minus v by c whole square minus 1. Now h nu on the left side is the energy of incident photon, h nu dash is the energy of the scattered photon, and the second part here, because the electron is also moving. So we have to write down the energy, kinetic energy part for that electron also, and because the electron now it is moving with relativistic speed, with the speed which is comparable to the velocity of light. So we have to write relativistic expression for kinetic energy, and this is the relativistic expression for kinetic energy, which is mc square into gamma minus 1, and gamma is this factor. So the thing is, we have to consider the relativistic energy expression. Now we can write down in terms of wavelength, which is h over lambda, because we can write nu as c over lambda. So h over lambda is h by lambda dash plus this again a factor of kinetic energy for the electron. So this is the conservation of energy part. Now on the right side, we can write down the conservation of momentum. So momentum, it's a we know it's a vector quantity, so we have to resolve this into component, and on the x along the x axis we write down p dash cos phi and p dash is the momentum of the photon and p is the momentum of electron. So we can write down on x axis p dash cos of phi plus pe cos of theta. Theta is the angle with incident direction and the motion of electron. And on y direction, we can write down this because initially the momentum is in the x direction. So we can write down 0 and we can write down the vertical component, the positive on the upper side and the negative on the lower side. And then we have to solve these equations, and we can put it into a simple problem, simple equation. And the equation is lambda dash minus lambda, and lambda dash is the scattered radiation and lambda of the incident one is equal to h over m into c into 1 minus cos phi. Now we can see h, m and c, or these are constant, or this lambda dash delta lambda, it depends on phi, the scattering angle. So we can say that the Compton shift, it depends upon the scattering angle and nothing else. Now this h over mc, since all are constant, we know well known this physical constant, this is called as lambda c Compton wavelength, and if we put the values we can get 2.43 picometer, which is very, very small. Now the Compton shift is responsible for this electromagnetic pulse caused by thermonuclear explosion in higher atmosphere. So since in higher atmosphere, if there is some radiation and they knock these electron, they will move, and when they move, they produce this electromagnetic field, which can interact with the field, which can interact with the circuits on the earth, and they can cause or they damage them. Now the next thing is why Compton effect is, we can observe Compton effect in X-rays and gamma rays. So we can get this answer from here. If we calculate the fractional energy loss, because from there to we can use any radiation, but why only in higher frequency, why only with X-rays and gamma rays, not with visible or ultraviolet or microwave. So we will get the answer from here. So, we calculate the fractional energy loss, that means the difference of energy, and then we write down in terms of lambda, and we will get this delta lambda upon lambda plus delta lambda. So, now this fractional energy loss, the energy that this photon imparts, this is equal to, this is inversely proportional to lambda. So, if lambda is more, loss will be more. So, it will impart less energy, but if lambda is small, like for gamma rays and high frequency. So, if lambda is less, the photon will impart more energy to the electron, and then we can see the difference, because if the photon impart more energy to the electron, so the photon will come out with lesser energy, and if it impart more energy to the electron, it will come out with lesser energy, and then we can see the difference between incident and the outgoing wave. Now, these are some problems on these Compton effect. So, we can solve this problem, and then it will be more clear. And there is a problem, the last problem, all the wavelengths are given in microwave, visible and ultraviolet, X-rays, gamma rays, and then from here we can calculate the energy loss, and then from the energy loss, from the percentage energy loss, we will see that the energy loss is more in case of gamma rays or X-rays. So, these are the books, Fundamental of Physics by Resnick, Halliday and Walker, Principle of Physics by Savay and Javed, Concept of Physics by H.C. Verma, then Introduction to Modern Physics by Mani and Mehta, and there is a book by Physics for Computer Science students, Garcia and Damask, and there is another book, An Approach to Physics, and this is mainly on problem. Thank you.
With this note, thank you, sir. Thank you so very much for giving us deep insight into the topic, that is modern physics. And I would like to tell you all, as Dr. Hussain himself said, that this was, because we have finished with the lecture, that this was the introductory lecture on modern physics. Tomorrow also, we would be talking more on the modern physics. Though with the help of this lecture, we were able to aware ourselves with the photoelectric effect as well as the Compton effect, as we have very less time left with us. In the brief words, please explain the basic difference between the photoelectric effect as well as the Compton effects, if you would like to tell the students.
Okay, photoelectric effect is like you have a metal surface, you shine light on the metal surface, the electrons, they are emitted, they come out from the on this metal surface, and if you have, as I have shown on the circuit, we can detect the current. In Compton effect, actually what happens, you have target, a material is there, and you incident these X-rays, and these X-ray, they collide with this electron of the target, and then this radiation, it comes out with lesser energy. And this is because photoelectric, the domain of photoelectric effect is ultraviolet and visible, because the work function of this metal is of this order, and this Compton effect, it is you can observe this Compton effect in with high frequency radiations, because the energy loss is more than there.
So this was the difference between the photoelectric effect as well as the Compton effect. Sir, you also use the term photon theory. What basically photon theory is?
Photon theory means particle theory. Like Einstein, he said that these light, it comes in the form of photons, energy bundles, like particles. So
we can say that it is all
or photon model, a particle model of light. So it behaves like a wave. In the beginning, we have discussed all these phenomena like reflection, refraction, interference, diffraction and all. So they all we can explain, or we can explain the experimental results of all that with the help of wave theory. But to understand the experimental result, or to explain what we are getting experimentally, this wave theory fails. We cannot explain by considering light as a wave. So we have to go for the photon or the particle model.
With this note, thank you, sir. Thank you so very much. And I would like to tell you all that if you want to access this particular lecture, you can definitely access us with the help of YouTube, because we daily upload our lectures on the YouTube, with the help of which you can revive what we made you learn. Thank you, sir. Thank you so very much. And also, we would be again tomorrow with Dr. Mohammad Mudassir Hussain, and we would be learning more on the modern physics.
So tomorrow we'll be talking on the other way. Like here we have considered light, wave as a particle. Tomorrow we'll be talking how a particle, it behaves like a wave.
Sure, definitely we would be talking more. Thank you so very much.